So I want to talk about ideal projectile motion and kind of, you know, describe that in some special cases of 3D motion, the horizontal projection of a trajectory or a flight path. So the x component of a horizontal trajectory, whether it's the vector position or the velocity or the position, okay, we know that it is constant in most cases. For instance, if we had a bullet, flying at this in this direction, okay, we can conclude that its x component is constant and its y component is continually changing. Now, with that being said, these are just ideal situations, okay? So an ideal projectile is any object that is released with some initial velocity, okay? Some initial velocity, and then moves only under the influence of gravitational acceleration. What I mean by that is this projectile is only influenced by the g component, by g, okay? Which in our case we're going to set g is always going to be equal to 9.8 meters per second squared, okay? All right, and ideal projectile motion neglects air resistance, okay, and wind speed. So the spin of a projectile and other effects influencing the flight of real life real life projectiles. Okay, there we go. These are typically not expressed ideally in real life situations. However, in this, we're going to neglect air resistance and neglect, how the wind will affect the specific projectile. So, therefore, the position function, or the position vector for projectile motion, can be expressed as our position function. Again, remember from the last video, our position function, all right, is equal to, we're going to express it in terms of x, comma, y, all right, which is equal to x hat plus y hat, and the velocity vector of this, is equal to the derivative of this business up here. So I'm just going to simply state it as the change in position over the change in time. All right, for the x component plus our y component, change in position over change in time. Position, okay, with respect to time, y hat. So, with that being said, the gravitational acceleration, all right, the acceleration of gravity is equal to 0. So there's no acceleration in the x component, comma, negative g, okay? I'm going to box that right there. This will be particularly important in our example in the next video. So with this being said, this can be expressed as negative g in the y component of our vector. Now with that being said, we know that since this is true, we know that the acceleration, the acceleration in the x component, okay, is equal to 0 meters per second squared. And our acceleration in the y component, is equal to negative g. Now in the last video, we talked about integrating upwards. Okay, so if we integrate this function, we will most certainly get, since our acceleration in the x component is 0 meters per second, this for typical trajectory with negligible air effect, with air resistance and negligible wind resistance, we can say that our velocity in the x component is equal to our initial velocity in the x component, and we can safely assume that when we integrate this upwards to the velocity component in the y direction, okay, we're going to get our initial velocity in the y direction, okay, our initial velocity in the y direction minus, remember we're integrating all this with respect to t. So minus g times the change in time when we integrated g up a level to velocity. Therefore, when we integrate up, remember from the last video we took those derivatives, when we integrate the velocity vector up, alright, we know that the position, the x position, is equal to, alright, our initial x position plus our initial velocity with respect to time. Remember, we integrated up with respect to time. And the same thing goes for this function right over here. We know that the y position, or in the y component, is equal to the initial y position plus velocity in the y direction, initial velocity times the change in time, minus 1/2 g delta t squared.